By now, the existence of quantum mechanics is a well-known fact. It is often characterized as the most advanced level of the physical sciences in existence, being often represented as the epitome of complicated and sci-fi. This, of course, is not actually the case, but quantum mechanics has earned this reputation from its mind-boggling nature and from the fact that classical physics does not apply to scales this small. Of course, the way we perceive classical physics is directly influenced by quantum interactions at attometre and Planck length scales. Technically speaking, however, quantum effects only start to become noticeable at these scales. Take, for instance, the Heisenberg uncertainty principle, which states that it is impossible to measure both an object's momentum and position to the same degree of precision at the same time. This, from the perspective of quantum mechanics, is entirely accurate. However, the Heisenberg uncertainty principle fully applies to macro-dimensional scales as well. It is impossible to measure the exact position of an object without compromising the uncertainty of the momentum measurement. However, such degrees of detail are negligible for everyday use. You must no doubt have heard numerous times that quantum objects can exist everywhere at the same time. Why then does a tomato not exhibit these quantum properties and exist in a superposition of positions? Well, it all boils down to information isolation, and that's what we will be discussing in this video. Let's first understand some of the fundamental properties of quantum objects before looking into why these properties do not apply to larger objects, or do they? One property of quantum objects is that of coherence, also called quantum superposition. According to popular belief, quantum superposition is the simultaneous existence of an object in multiple states at the same time. This is not the case. Rather, it is simply when there is greater than a single possible outcome to the measurement of a particular quantum particle. When the particle has not been measured and is allowed the luxury of probability, we say that it is in a state of coherence. Likewise, when the particle is measured and we can be certain about which state the particle was in, we say that it has collapsed into a single state or decohered. Quantum decoherence is a near instantaneous process. An electron can decohere in less than 10 to the negative 31 seconds. That's less time than it takes a photon to cross the width of a proton in a vacuum, which takes 3 times 10 to the negative 24 seconds. This must not be confused with what occurs in the realm of classical physics. In classical physics, everything is in a definite state. It is either in this location or the other, either red or blue. If there's any mystery about what the state of the object is, then it's only because of human ignorance. In the quantum world, on the other hand, the definition of the property itself is ambiguous, it's ill-defined. It is this property of quantum superposition that makes quantum objects so distinctly quantum. This gives rise to an interesting question. How do we find out if a quantum object was in a superposition in the first place? When an object in superposition is measured, it produces only measurements, concrete values. Thus, if we were to measure a quantum object, then we would only receive single, certain values that would tell us nothing of the object states before the measurement, only after. Well, as long as we don't try to measure that specific property of the quantum object, the multiple possibilities for the outcome of the measurement behave like waves and interfere with each other. They get added or subtracted from each other through interference. This is the origin of the term quantum superposition. To add two waves together is to superpose them. So we've now established that superposition is the delicate state, and an object will collapse into decoherence if it has any interactions with its environment that could be deemed a measurement. This brings us to an interesting question once more. What exactly is a quantum measurement? How does a quantum particle know that it is being measured? We must first understand what exactly a measurement refers to in this case. Contrary to popular belief, a measurement does not imply that a conscious mind be present to interpret physical happenings. There is no experimental evidence that suggests this, in fact. The presence of a conscious mind does not change the outcome of reality. Werner Heisenberg, one of the pioneers of the Copenhagen interpretation of quantum mechanics, wrote the following. Of course, the introduction of the observer must not be misunderstood to imply that some kind of subjective features are to be brought into the description of nature. The observer has rather only the function of registering decisions, i.e. processes in space and time, and it does not matter whether the observer is an apparatus or a human being, but the registration, i.e. the transition from the possible to the actual, is absolutely necessary here and cannot be omitted from the interpretation of quantum theory. John Bell, the founder of Bell's theorem, put it more bluntly. Was the wave function waiting to jump for thousands of millions of years until a single cell living creature appeared? Or did it have to wait slightly longer for some highly qualified measurer with a PhD? This idea can be directly linked to, in physics, of the so-called observer effect. In effect, the observer effect states that there are certain physical processes that involve interfering directly with the object under measurement, thereby changing the measurement's outcome. Here's a simple example of this. To measure the pressure inside a tire, the pressure valve must first be opened, letting out some of the air inside and changing the pressure within the tire. Thus, it changes the outcome of the measurement itself. How then does the quantum object know that it has been measured? A measurement is simply an interaction. The many worlds interpretation of quantum mechanics, also called the Everett interpretation, suggests that each time such an interaction occurs, as many parallel universes as quantum states that existed were created, thus causing the object to collapse into all the states at the same time. Regardless of this, both the Copenhagen and many worlds interpretations of quantum mechanics are simply interpretations. It does not matter which one is right because they both produce the same outputs. What matters is which one is more logical. We've now established that decoherence occurs when a quantum object or a set of entangled quantum objects, also called a quantum system, interacts with another quantum object or a set of quantum objects. Thus, it's only logical to state that as objects grow larger and more complex, they are prone to more interactions with their environment, causing their plunge into decoherence. While it becomes harder to maintain the coherent quantum states of objects as they grow larger and larger, we're yet to find out if there is indeed a physical limit to how these quantum effects can scale up. This key principle to preserving coherence in an object is known as information isolation. To informationally isolate an object, one must ensure that there is no record made anywhere in the universe of the properties of whatever object we're referring to. Let's say it's a quantum tennis ball. The object must first be placed in a complete vacuum where there is an absence of bosons and fermions. This is so that the trajectory of these particles upon their collision with the tennis ball cannot be traced back, thus leading one to find the trajectory of the tennis ball. Likewise, the object must be placed in absolute zero Kelvin, to avoid black body radiation. This would result in the object constantly emitting photons, which could be used to find the trajectory and properties of the object. It is this near impossibility of informationally isolating a macro-dimensional object that makes large objects decohere and lose their quantumness. However, physicists are ever conducting experiments to find out if there is indeed a limit to how much this quantumness can scale up. Is there a fundamental limit to how quantum properties can scale up? Or will they simply lose their quantumness at some particular size limit? In 1999, researchers at the University of Vienna succeeded in getting 60 atom-large molecules called fullerenes to go into quantum superposition and got them to exhibit an interference pattern when subject to the double-slit experiment. These molecules were 0.7 nanometers across, much larger than an atom. In 2019, the same research team created quantum interference in molecules 430 atoms large, that's 6 nanometers across. Last year, in 2021, researchers managed to induce quantum behavior in a 2000 atom large molecule called gramicidin A1, a naturally occurring peptide. However, this breakthrough seems minuscule when compared to what physicists managed to achieve. They managed to send nanoscale silica crystals 140 nanometers across into quantum superposition. They cooled the particles down to their quantum ground state a few millionths of a degree above absolute zero and put them into a very high vacuum. Normally, when such large molecules like this one which have over 100 million atoms, are fixed into position, levitating in the air, an apparatus known as an optical trap is used. These are essentially like laser tweezers, fixing the objects tightly in position. However, these can interfere with the quantumness of the object being levitated. Now, with their recent development, researchers eliminated the optical trap altogether, instead coaxing the object into position using an electric field. In the future, physicists hope to find out if there is any limit to how quantum effects can scale up, and they will attempt to make Schrodinger's cat a reality. Starting with tiny living organisms such as viruses and tardigrades, and then scaling up their experiments. However, one must account for the fact that an object's associated wavelength, also called a matter wavelength, is inversely proportional to its mass. As we scale up objects, their quantum interference will reduce to a near negligible point. If we find that quantumness can continuously be scaled up, the difficulty of ensuring an object's quantum coherence could mean that we could design extremely delicate sensors that could detect gravitational waves. The possibilities are simply endless. Whatever the case is, we must continue to probe the limits of the quantum world, learning more and more about the fundamental nature of reality itself. Thank you for watching.